What if I told you that a company just raised $200 million to store electricity using giant spinning wheels? And these wheels can operate for 25 years without breaking down, potentially solving one of renewable energy's biggest challenges. Welcome to episode 24 of the Curiosity AI podcast. I'm here to break down the most fascinating technological breakthroughs that are shaping our future. Today, we're diving into something that sounds almost ancient, but represents cutting-edge innovation. In Utah, a company called Torus has convinced sophisticated investors to bet $200 million on Flywheel energy storage technology. While everyone else is focused on building better batteries, Torus is scaling up massive spinning wheels to store electricity for the electrical grid. This isn't just another startup story. Their systems are already powering Salt Lake City Airport, and they've secured contracts for 500 megawatts of utility-scale deployment. Let me explain how this technology works, why major investors are backing it, and what it means for the future of renewable energy storage. Here's the fundamental challenge with our electrical grid. Electricity must be used the exact moment it's generated. Unlike water or gasoline, we can't easily store electrical energy for later use. This creates massive problems as we add more solar and wind power. Solar panels produce peak electricity at midday when demand is often lower. Wind turbines generate power when it's windy, not necessarily when we need it most. Traditional lithium batteries can help, but they have serious limitations. They degrade quickly under constant charging and discharging. They typically need replacement every 3 to 5 years, and they respond slowly to sudden changes in grid demand. Torus took a completely different approach. They store energy as mechanical motion in massive steel wheels, spinning at incredible speeds. When excess electricity is available, electric motors spin up these wheels. When the grid needs power, the spinning wheels act as generators, converting their motion back into electricity almost instantly. Think of it like a potter's wheel that keeps spinning long after you stop pedaling. Except these wheels are engineered to spin for hours and release their energy on command. The breakthrough isn't just the flywheel technology itself. It's how Torus combines flywheels with traditional batteries in what they call a hybrid system. The flywheel component, called Nova Spin, handles rapid power fluctuations and provides millisecond response times for grid stabilization. The battery component, Nova Pulse, provides longer-term energy storage. This division of labor dramatically extends the chemical battery's lifespan while giving grid operators the fast response they need. Here's where it gets really interesting. While chemical batteries wear out from repeated cycling, these mechanical systems are designed to operate for 25 years with minimal maintenance. The wheels spin in vacuum chambers to eliminate air resistance and use magnetic bearings to reduce friction. Time magazine recognized this durability by including Nova Spin in their Best Inventions 2024 list. But the real validation came in September 2025, when Magnetar Capital invested $200 million in the company. This investment reflects broader geopolitical tensions in energy storage markets. China currently controls 55% of the global battery manufacturing capacity, creating supply chain vulnerabilities for Western countries. The Chinese dominance extends across the entire battery value chain, from lithium mining to cell production. Flywheel technology offers an alternative path that uses common materials like steel rather than lithium, cobalt, and rare earth minerals with constrained supply chains. For American grid operators and European utilities, this represents potential independence from Chinese battery manufacturing and the associated geopolitical risks. The economics become compelling when you examine the total cost of ownership over decades. One flywheel system operating for 25 years could replace 5 to 8 battery systems over the same period. While the upfront capital costs may be higher, the elimination of replacement cycles could deliver substantial savings, especially when considering labor costs and system downtime during battery swaps. Torus reports their systems achieve 99.9% uptime across more than 230 installations completed in 2025. This reliability metric is crucial for utility customers who need absolute certainty that grid services will be available when required. Compare this to battery systems that experience performance degradation and increased maintenance needs as they age. China isn't ignoring Flywheel technology either. They connected a 30-megawatt Flywheel project to their grid in 2024, representing the largest single installation announced globally. Even more ambitious is their 200-megawatt hybrid Flywheel battery facility under construction in Shaanxi province. This suggests that Flywheel storage is transitioning from experimental technology to commercial viability on both sides of the Pacific. The international development validates the hybrid approach that Torus pioneered. Rather than seeing flywheels and batteries as competing technologies, the industry is recognizing their complementary strengths. This technological diversification mirrors what we're seeing across renewable energy, where different solutions excel in different applications rather than one technology dominating all markets. Let me walk you through the specific applications where this technology excels and why customers are choosing mechanical storage over traditional alternatives. Grid stabilization represents the primary market opportunity. Modern electrical grids require numerous ancillary services beyond simple energy storage and discharge. Frequency regulation maintains the grid's 60 Hz frequency as electrical load and generation constantly fluctuate. Voltage support maintains proper voltage levels across transmission and distribution networks. Reserve services provide backup power when generators unexpectedly go offline. Torus Flywheel systems excel at these services because of their millisecond response times and exceptional cycle life. Traditional generators take minutes to start up and reach full output. Chemical batteries may take seconds to respond to grid control signals. Flywheel systems can inject or absorb power almost instantaneously, making them ideal for maintaining grid stability in real time. Data centers represent another compelling application that's driving significant adoption. These facilities consume enormous amounts of electricity and experience dramatic load fluctuations as computing demands change throughout the day. They also require uninterrupted power supplies and backup systems for when the grid fails. The hybrid Flywheel battery approach provides both instant response for sudden load changes and sustained backup power for extended outages. Salt Lake City International Airport is already using Torus systems for exactly these applications, both power quality management and emergency backup power for critical operations. Industrial facilities are implementing the technology for peak demand management, also called peak shaving. Manufacturing plants often face demand charges based on their highest power consumption during monthly billing periods. These charges can represent significant portions of their electricity costs. By storing energy during low-demand periods and discharging during peak consumption hours, facilities can dramatically reduce these demand charges. Ash Grove Cement and other industrial clients are reporting substantial cost savings through strategic load management using Torus systems. Renewable energy integration presents perhaps the most important long-term application. Solar and wind power create grid instability due to their variable and sometimes unpredictable output patterns. Cloud cover can reduce solar output by 80% in minutes. Wind generation can ramp up or down equally quickly based on weather conditions. Flywheel storage can smooth these fluctuations while storing excess energy during periods of high renewable generation. The fast response times help grid operators maintain stability even as renewable penetration increases toward 50% or higher in many regions. Port operations are also discovering Flywheel applications. Large cargo handling equipment creates massive power demands that can stress local electrical infrastructure. Flywheel systems can provide the instant power required for crane operations while managing the impact on the broader electrical grid. Torus has announced ambitious expansion plans that will test whether mechanical storage can scale to become a significant portion of the energy storage market. They're targeting over 1 gigawatt of quarterly capacity deployment within 3 years, which would represent massive growth from their current installation base. The company is developing a manufacturing campus called Giga1 to support this expansion. This facility will need to produce the precision steel components magnetic bearings, vacuum chambers, and control systems required for flywheel storage. The manufacturing complexity represents both an opportunity and a significant scaling challenge. The $200 million Magnetar investment will accelerate deployment of what Torus calls modular power plants across utilities, data centers, and industrial facilities. They've secured binding agreements with PacifiCorp for up to 500 megawatts of demand response capacity, demonstrating utility-scale commercial traction. However, significant engineering and business challenges remain. The precision manufacturing required for flywheel systems is substantially more complex than battery assembly. Supply chain development for specialized components like magnetic bearings and vacuum chamber systems needs major investment and could constrain scaling timelines. Market education continues to be important. Many utility engineers and grid operators have decades of experience with traditional generators and increasing familiarity with battery storage systems. Flywheel technology requires different operational understanding and maintenance approaches. The competitive landscape is evolving rapidly as well. Lithium battery costs continue declining due to manufacturing scale and technology improvements. New battery chemistries like sodium-ion, solid-state, and flow batteries may address some current limitations of chemical storage. Torus must continuously improve their technology and reduce costs to maintain competitive advantages. Regulatory frameworks also need development. Grid interconnection standards, safety regulations, and utility procurement processes were largely designed around traditional generators and chemical batteries. Mechanical storage systems may require new standards and approval processes. International expansion represents both opportunity and complexity. Different countries have varying grid codes, safety standards, and utility market structures. Successfully scaling globally will require adapting the technology and business model to diverse regulatory environments. Despite these challenges, the fundamental value proposition of 25-year mechanical storage systems appears compelling for many grid applications. The combination of fast response times, exceptional longevity, and independence from constrained material supply chains positions flywheel technology as a valuable complement to chemical batteries, rather than a complete replacement. The success of Torus in attracting substantial investment and securing utility-scale contracts demonstrates that energy storage markets will likely support multiple technologies rather than a single dominant solution. Grid operators are becoming increasingly sophisticated about matching storage technologies to specific applications where they perform best. The 25-year operational lifespan addresses one of the most significant economic challenges facing energy storage deployment: the recurring costs and operational disruption of frequent equipment replacement. For grid applications that prioritize reliability, predictable economics, and fast response over maximum energy density, mechanical storage offers compelling advantages. This represents a broader trend in energy technology, where innovation often comes from reimagining proven concepts with modern engineering precision. Flywheel energy storage has existed for centuries, but combining it with magnetic bearings, vacuum chambers, precision manufacturing, and sophisticated control systems creates entirely new capabilities. As our electrical grid continues evolving to accommodate higher levels of renewable generation and increasingly complex demand patterns, storage technology diversity will prove more valuable than any single solution. The hybrid approach pioneered by Torus shows how different technologies can work together rather than compete. What's fascinating is how this challenges conventional thinking about technological progress. While most companies chase incremental improvements to lithium batteries, Torus found opportunity in scaling ancient mechanical principles to modern grid demands. What's your take on this approach? Do you think mechanical energy storage has a significant role alongside chemical batteries in our renewable energy future? How important is technology diversity versus focusing resources on a single dominant solution? I'd love to hear your thoughts on whether this represents genuine innovation or expensive engineering that will struggle against declining battery costs. Don't forget to subscribe for more breakthrough technology analysis that challenges conventional wisdom, and I'll see you in the next episode where we continue exploring how unexpected innovations are reshaping our energy future.